Hello, everyone, and welcome to Africa Fire Mission's weekly virtual training session. My name's Mike, and I'm the programs director here at Africa Fire Mission. And we're so happy that you took time out of your busy schedules to join us for today's training. Today, we're going to be wrapping up what was a three-part series we were doing on fire dynamics. So, this is a deep dive sort of into um, some studies that were done that are starting to apply science to firefighting. And our last two sessions were led by Chief Mark Vanderfeist, and he started out talking a little bit about fire behavior as it relates to fire dynamics. Last week, we dialed down one step closer, and we're looking at fire flows, and we were looking at which branches we should be using, okay, uh, and that sort of stuff with the water application. Now we're going to go one step deeper. So we're looking at firefighting through the microscope, right? And that first one we zoomed all the way out. Last week we zoomed in a little more. This week I'm going to zoom in real close. We're going to be talking about a concept called water mapping. And what water mapping is figuring out where exactly that water is going to go as we apply it to the fire, and how can we most efficiently apply that water to the fire. Now, this comes from studies that were done here in the US. Um, so we're gonna jump right in to our class here, because we may run a little bit over for today, but there's a lot of good material here that I want to be sure that I cover. Okay. Uh, as usual, please introduce yourself in the chat. I'm going to try to keep an eye in the chat and see if there's any questions. Let me know as we're going along. I'll try to address those. As we transition into tea time at the end of the class here, you'll be able to answer or ask any questions that you like. So we're taking a look at these hose stream mechanics. Okay. And I said, this is studies. All this information is available at fsri.org, and that's the Fire Safety Research Institute. fsri.org. We'll drop that in the chat for you. They did these studies applying science to how we fight the fire. So this is looking at their information about hose stream mechanics. All right. The first thing that we're going to talk about, air entrainment and hose streams, and what um, this is what we're talking about here is air joining in with the fire stream as we're spraying that water. How much air is getting sucked in with that water, and what is that air doing to the fire or to the situation that we're in, right? So do do branches move air? Does a fire nozzle, does a fire branch, does it move air? Okay. If we take a look, well, sure, we do hydraulic ventilation. We'll talk about that maybe a little bit toward the end if we have time. That's where you use the hose stream set on a fog pattern to vent the building. But can we push fire? Can we move the fire around with our hose stream? Something that we always talked about here in the US was, if you attack the fire from the outside, could you push the fire? And will that make things worse for the victims inside the building? So if you take a look uh, at the bottom of the screen, the two images, one on the left-hand side is a video that's like the top of at the bottom of a stairwell, okay, looking up a stairwell where there's a fire. And then there's the thermal imaging images on the right-hand side. And when we watch this video, okay, they're going to apply a hose stream from the exterior, and you see how all that smoke and stuff and heat is blowing out up those, down, up or down those stairs, right? And that's a result of the hose stream. So, can we push the fire? All right. Is that really a thing that we can do with our hose line? Well, here's the full story. Okay, and if you look at this video that's going on here, they're applying a stream from the exterior, and look at how they're putting that jet stream or that straight stream in the window. They're not moving it around much at all. Uh, nothing really happened with the fire down below. Okay, we didn't see that fire push, we didn't see that fire move. All right, straight stream. Now here they're using this fog pattern and they're covering the whole window opening with it. And look at what it's doing inside the building. That's where it's pushing that fire through the stairwell. All right. So they're using this fog pattern, this wide pattern, covering the whole window opening. And what's happening there is it's entraining air, it's pushing air into the building. And that air pressure that they're adding into the building using that hose technique is what's trying to move that fire. That fire is trying to find a different place to go because it was venting or exhausting out of that window until they sealed it with the hose stream. Okay, so using the proper technique with our hose stream, that's what's gonna move things around. So they did these studies, all right, of air entrainment. They used a whole bunch. They did 78 different experiments, all sorts of different branches and things like that. That's where they got some of this information about how the hose stream, how the water stream flowing through the building can also move air. And I'm going to just skip over some of this stuff, but just to give you an idea, look, they used all these different nozzle branches, operating at different pressures, operating at different flow rates. This chart, I want you to take a look at this chart here. Okay. This chart is showing you on the left-hand side, these are our combination nozzles that can make a wide pattern or a narrow straight stream, compared to the chart on the right, which is just a jet nozzle or a smooth bore nozzle. Okay. The average airflow, look how much lower it is with that straight stream, jet stream, smooth bore nozzle than it is with the combination fog nozzle. And then when you look at if you set that on a narrow fog pattern, so the water's spraying out in a cone, and then you move that in an O-shaped pattern, move the branch around in an O-shaped pattern with a wider with a fog pattern. Look at how much air, the amount of air that you're forcing in there, it's up there 15,000 cubic feet per minute of air movement. That's as much as setting a power fan at the front door blowing into the building. So, how does that affect what we do? What should we think about that air entrainment? Okay, what they've learned was doesn't matter who manufactures the branch, all of them, the air entrainment is roughly the same amount. Okay, the faster that you move that branch, the faster that you whip that water around, the more air is going to get entrained or pushed into the building or sucked into the building. Okay, entrainment increases with a more broken hose stream. So when we're using the smooth bore, the jet stream, whatever you call that, that gets the least amount of air added into the fire and then as you move up to a combination nozzle set to a straight stream, then the narrow fog pattern, then the wide fog pattern. That's what impacts. That's how it grows the amount of air that's going to get moved into the building. Okay. Uh, so it's roughly the same, regardless of what pattern you're waving that hose around in. Sometimes we do a wall, ceiling wall. Sometimes we go in a circular pattern with the branch. Sometimes we make sort of paint the letter Z as we're whipping that around. It doesn't matter what pattern, it's the speed that impacts it. And then, as we said before there, that can just the branch can meet or exceed the power of a positive pressure ventilation fan set at the front door. So how we move that nozzle or that branch and what pattern of water we're putting in the building really controls how air moves through the building as well. Next thing we're going to look at here is water distribution in compartments. So how does the water move around? We're spraying water into the building. How does it distribute itself throughout the room? Okay. Again, did a whole bunch of testing. I'm not going to spend a lot of time on this, but I just want you to see they're using this scientific process. They built these rooms within a giant warehouse where they do this testing. They used some equipment. Here they're doing 82 different experiments to figure out where the water goes. This is a little floor plan, right, of the sort of simulation rooms that they built as they were doing this testing. And then this is the neat thing. This device that you're looking at here, they're calling it the actual delivered density apparatus. This is a testing piece of testing equipment that they usually use to test the overhead sprinkler systems that are in buildings. And what you're looking at is just a set of collectors that are going to collect water as it's sprayed into the room. It collects the water and sees how much water, is distributed in different places throughout a room. And again, normally they're using this for sprinkler systems. They repurposed it to see when we put water in the building, where is that water going to go? Okay. So they've repurposed this equipment. Now, then they're going to do some testing. They're going to try things out to see how it works. On the left, we're going to have a little video where they're applying water from the exterior of the building with a straight stream from the window. And you've got this fire burning uh, right in the dead center of the room. On the right-hand side, it's the same thing, only they're going to use a fog pattern from an interior doorway. All right, let's take a look here. The video sort of flips to the side, right? But the fire's going as they're spraying the water into the window with that straight stream. You can see how it's difficult to get water directly on that fire. All right, so you see the water's being sprayed in the window, directed, sort of up toward the ceiling. Really didn't have a whole lot of impact on that fire that's only burning in the center of the room. Now, if we look at the other side, same thing. They're using that fog, a wide fog pattern directed up at the ceiling. Look at how it's moving, how the water's dispersing. Okay. It's not it's not hitting the ceiling and bouncing right down on top of the fire. Those are things that we sort of thought were happening before, right? And we trying to figure out how does the water move when we're putting it into the building. And what we've learned is that it has a lot to do with momentum. Okay. Momentum, if we're looking at that scientifically, momentum is the equation for momentum is mass times velocity. Mass times velocity gives us the calculation for the momentum of it. And the water that we're moving is very heavy, and it's moving very fast as we discharge it from our branch, from our fire hose. Okay, so it's got this momentum and it likes to stay moving. All right, so what we thought was in the past, we had thought, if you spray that water directly straight ahead, 90 degrees directly at the wall in front of you, it's going to bounce off of that wall. Or if you spray it at an angle up at the ceiling, it's going to bounce off of the ceiling and then rain down on the room. But this testing has showed us that that's not the case. The momentum of the water is going to continue. So when we put that water, if we spray that at that 90-degree angle directly at the wall in front of us, when it hits that wall, the momentum is going to carry it out in 360 degrees, and it's going to cover the entire surface of that wall until it either hits another wall or some kind of obstruction, or the forces of gravity are going to pull it down, slow it down, and stop it from flowing. All right. So now that we know that, how do we maximize our efforts when we're applying that water to the building? Okay. So what it's telling you here is direct your water at the steepest possible angle that you can to the ceiling. And that's going to give you the greatest surface coverage and maximum cooling. Now, we're going to show you that in some videos later. But what happens is you're directing that water at a steep angle at the ceiling. That water is going to spread out and cover that 360 degrees, spreading out, covering the entire ceiling until it hits the walls. When it hits the walls, the momentum of that water is going to run down those walls. So by directing the hose stream straight up at the steepest possible angle we can at the ceiling, that's going to cool all of the surfaces in the room, the surfaces of the ceiling and the surfaces of the walls all at once, which is going to rapidly cause gas contraction. Everything's going to suck down in, and it's going to drop that. It's going to cool, it's going to give us our maximum cooling benefit than just applying the water in the window, whipping it around, or something like that. Then, after we've done that steep angle at the ceiling, then we need to get water onto the burning fuels that are burning in the building. So the first thing we're doing, we're cooling the ceiling and all the walls by applying the water at that steep angle. Then you're going to bounce that off of maybe the window opening. In this video that's playing here, you see they're bouncing it off of the side of the door entry position, and that's diffusing the water, causing it to splash and splatter around and then wet the burning fuels. So we're going to have a couple different videos coming up here to show you these principles, all right? So this first one, we're looking at providing that steep angle. So here we go. He's opening up the hose stream. He's directing it at the back. Notice they've made the walls clear so you can see through them. And the water's only hitting that back wall. But as he increases that angle, starts spraying that water steeper, all right, you can see, maybe it's difficult for you to see, but that water is cascading down the sides and down the walls. All right, so he's wetting the entire ceiling surface. He's also wetting the side walls and the back wall, all by directing that at the steep angle. So watch, now it's only wetting the back part of the room because he's at that shallow angle, spraying it towards the back. So most of our water is covering the back wall and the back corners. Watch as he increases the angle of that hose stream and it gets steeper. Watch how the water starts moving out along the walls. Okay, spreading 360 degrees out all over. Now we've got the water running down the side walls as well. The water's cooling the ceiling, cooling the back wall, cooling the side walls, all at the same time. All right. Very valuable to know, okay, look at how we can get this maximum amount of cooling by directing that at the steep angle. Now we're looking at it from the inside. He's spraying at the back. It's cascading down those back walls, but not really getting the side walls wet. As we increase that angle, now it's raining down the walls. It's getting the camera wet so we can't see. We're getting every surface in that room coated and cooled with water by applying at that steep angle directly inside the window. All right. Next one here, this is what we're calling this lintel hit. So here, he's bouncing it off of the top opening of the window. And instead of that water going up to the ceiling and running down the side walls, it's dispersing the water and it's putting that water onto the objects that might be burning in the center of the room. So instead of the water cascading down the walls, it's dispersing and sort of bouncing off and splashing down on the things that are on the floor. All right. So those are different places. So you'll start with that steep angle to the ceiling, watch the fire darken down and cool things off, then bounce it off of something else, or follow-up action, just walk up to the window and spray in the window. Okay. And I think we'll see that in a later video here as well. If you're heading down a hallway, here he's heading down the hallway. By hitting the water off of the open door, you've got a door opening there, and he's spraying water against that the door opening there. Look at how the water's deflecting off of that and dispersing throughout the room. So there we can cool the contents of the room without getting into it. This is very valuable if you don't have a breathing apparatus. Maybe you could be out there in the clear air and get that fire knocked down from the hallway by putting that water sort of at an angle and washing it up and down in that doorway. Right? What are our takeaways that we should have from our water distribution? Right? Um, Streams from either the window or the doorway show similar distribution on the plane. What does that mean? It doesn't matter whether we're applying that water from the doorway inside the fire building or whether we're applying it from a window from the exterior, we can still distribute that water the same way throughout the room. So it doesn't hurt. Matter of fact, it's encouraged that if we see that fire from the exterior, that we make our exterior attack first. All right. Now, in these studies, the size of that compartment does matter. This study was looking at residential sized rooms. And what we've found with residential sized rooms is that the momentum of the water moving and how far that water will carry, okay, is going to usually exceed the size of an average residential room. So things would change a little bit in a commercial structure where the rooms are much bigger. But your hose stream will outreach the size of a residential room. So we're not in those residential settings or where there are small rooms, we know that our hose is going to reach. We know that if we do that steep angle to the ceiling, that momentum of the water is going to carry it all the way across the ceiling and down the walls around it. Um, the greater distance you are away, more dispersion, right? So if you're aiming that hose line into that second floor, all right, you're gonna lose some of the momentum of the water the farther it has to go before it strikes that surface. So if we're shooting water into the second, third floors, all right, you're gonna lose some of that momentum, which means that you're gonna get less surface coverage with that technique, but you're gonna get more dispersion. It's going to spread out more. It's going to rain down more. Not so that's not telling you don't use that technique, but just to think about it, the higher up you go, the less effective it will be. All right. How do we get the most coverage of surfaces within that burning room? It's that steep angle that we're doing it, okay? The shallower that angle, the further back in the room we're aiming that hose stream at, that straight stream or that jet stream, the shallower that angle is, the less surface coverage we're getting, okay? It's difficult to get water into the middle of the room with the max angle only. As we're doing that steep angle, we're coating the ceilings, we're coating the walls, but it isn't getting water onto the burning stuff that's in the center of the building. So we need to be sure that we can get in there with a follow-up and then put water on the stuff that's in the middle of the room. And then the last thing where it talks about creative methods that result in better follow-up distribution. This is where it's up to you guys, okay? Once you've cooled that room from outside using the steep angle and cooled all the surfaces, how are you going to follow that up and get the water on the stuff that's actually burning? And that's where you're bouncing it off the lintel, bouncing it off the window openings or the door openings, or maybe it's just that you're getting in there and moving the hose stream around, okay? Uh, So suppression tactics, advanced techniques. How are we moving with the hose line through the building? Okay. This video is showing you what they call flow and move, where you're going to open up the hose stream, and as you're moving down the hallway, uh, you're going to be flowing water as you're moving. All right. Here, when you watch these guys do this, they're going to be working that nozzle in it or that branch in a pattern as they go. And if you think about what we were talking about earlier, okay, as we move that nozzle, that branch in the circular pattern, as we whip that hose stream around in a pattern, that's going to help to entrain air, which sometimes is a bad thing, putting air into the fire room. But as you're working your way down the hallway, if you're entraining air with you, you're pulling fresh air from in behind you into the fire compartment and into the room. So as you're moving down that hallway, if that hallway is smoky and has a light smoke condition, you don't have breathing apparatus. If you're using that stream, moving it in a pattern where you're getting lots of air entrainment, that's going to be drawing the fresh air in behind you that might let you get closer to the doorway of the room where the fire's at. Then you can do the dispersion technique off the side of that, and maybe that lets you get a little bit deeper into that building without putting yourself into harm. Okay. The other style of movement that we did before, um, shut down and move. So in this one, they're going to move the hose line in. They're going to whip they're going to move it around. Then they're going to shut it off and move some more. Okay. So they're going in, applying a little bit of water. Then they're going to move, stop, apply some more water, stop and move, shut down and move. Um, what these studies have showed us is that that is a little bit less effective. Things are going to be better, have a better impact on the fire, going to have make the conditions more tenable for you inside, and are going to make things better for the victims inside if we're using the flow and move. Well, which one's easier to execute? Spray, shut down, then move the hose, or try to move the hose while you're flowing water. Okay, it's going to be more difficult to do the flow and move. What does that mean for you? That means you've got to practice it. You've got to be out there working on how can we advance the hose while we're moving and flowing water. Right. Next, we're going to look at exterior water application. Okay, so here you're coming up to the window, steep angle to the ceiling. Watch how at first it has no impact, but then look how it dies down, right? That cooling, you can see some gas contraction, that smoke and stuff is pulling back inside. After you've applied that water, you've got to follow it up. All right, so you've done it, the steep angle to the ceiling. You see how effective that was, really knocks down that fire. Now they're going to go inside and do some kind of follow-up action. We should be able to tell by the smoke that we see when they see the fire starting to build back up on the inside there. It knocked the fire down enough to give them time to get in, and right away they're there, they've found the seat of the fire, and they're putting water on it from the inside with that follow-up. So what we're doing with that exterior water application, we're buying us some time, resetting the fire to those pre-flashover conditions, making it more tenable for the teams that are going to go inside. Okay. Again, here we're going to do exterior water application, and they're going to follow it up. So he's doing that steep angle. It's not working, not working, but here it is. It's suppressed it. Look at the gases sucking back in. Now he's doing the direct follow-up, going right in the window, moving that hose stream around, and soaking down those burning materials that are inside the contents of the room. Okay, so you don't always have to go around and go inside to do that follow-up. We need to do the follow-up, but you see how effective we knocked that fire down with the steep application of water to the ceiling, followed it up by sticking our head in there, moving around, dispersing that water on the burning items, the burning materials within the building there. Okay. Water usage, okay, as we're using temperature reduction, this is what we're really going for here. The timing of this is important. It's about getting water on the fire quickly. What's the quickest way that you can get water on the fire? Is it from the interior? Is it from the exterior? Every single fire is going to be different. But the key takeaway I want you to take with this is don't wait to put water on the fire. If you guys jump onto YouTube or any kind of social media and start looking around for firefighting videos, you're going to find all sorts of videos. The fire brigade is outside. They're getting hoses stretched. There's fire blowing out of windows. lots of visible fire, and they're fooling around, waiting, and then going in the door and going inside to get after that fire. What we've learned from these studies: rapid water on the fire makes it better, puts the fire out faster, makes it better conditions for us inside, makes it better conditions for any victims that may be inside. Quick water on the fire. That's the takeaway. All right. As we get that quick water on the fire, it reduces the heat release rate, something that Mark talked about. If you haven't watched our two other classes on fire dynamics, please go back, go to YouTube, Africa Fire Mission, check those out from the last 2 weeks. All of this ties together with what we're talking about here. Rapid water on the fire reduces the heat release rate, reduces temperatures within the rooms, reduces the rate of toxic gas production. That's making everything better for us and for people in the building. Okay. The timing is important. We're getting water on the fire quickly, and then we're following it up. All right. When we're using these, okay, how much water is used? Now, this is in gallons per minute because these were American studies, right? But 150 gallons per minute flow rate they used for all the experiments, and they were getting very rapid fire knockdown very quickly. Um, by using that volume of water. Okay. So it's not that much. You can really, and you guys are dealing with limited water, right? So we're talking around uh, 600 to 700 liters per minute. Okay. Um, so we can get that rapid knockdown without using a lot of water if we apply using the smartest techniques. So instead of just spraying that water everywhere that we see fire, use it appropriately, direct it at that steep angle to the ceiling, cool all those surfaces, and then follow it up. You're going to find that you're going to reduce the amount of water that you're using. How many of you guys have access to unlimited water, right? You've only got a couple minutes worth of water in a lot of your engines, right? This is going to help by using our brains, applying this tactic. You can see it's a lot deeper than just putting the wet stuff on the hot stuff, right? We're using science. We're looking at this. Now, even though we know that we're not using a whole lot of water, right? We still need to try to establish some kind of a water supply, or deploy a backup line or something. So try to get an extra line in service if you can. I understand that's difficult. You're dealing with limited resources, but you should still be thinking about this. What do we need for more water? How do we get that more water? Are we calling for a water bowser, some sort of water delivery vehicle that can bring us extra water, whatever that may be. Maybe it's what we'd call mutual aid, where we're calling the next over county. We're still thinking about that. Okay. Uh, Water can impact the flow path. Now, what is uh, what is a flow path, right? So a flow path, we touched on this a little bit in the last 2 weeks, but that fire needs uh, to flow. The airflow, there's got to be air flowing into the fire. Okay, as the fire burns, it's going to draw air to it. It's eating up that oxygen. It's breathing in that oxygen as it's growing, as it's burning, and it's exhausting or breathing out that smoke, unburnt materials, heat, all that stuff, right? So that's the flow path, is where that air is moving through the building, where it's coming in, where it's going out of the building. Where it goes in, we call that the inlet flow path. Where it comes out of the building, it's the exhaust flow path. In this picture, in that room at the top, okay, there's only one opening. There's a window there, but the window is closed and intact. So uh, the doorway that's open is serving as the inlet flow path, and it's also the exhaust flow path. Where those meet is what's called the neutral plane. So you'll see smoke layering up above in the exhaust flow path as it exits out over your head, and the fresh air is coming into the fire through that inlet flow path. Okay. But our water application can interfere with that. We saw that in that first video, right? We one of those first videos we saw that where when you were putting the wide fog pattern over the window or over the opening and completely covering it and moving it around, it sealed that off, and then that was making the fire had to find a different exhaust path. So that's where it was going out those stairwells. So that's where it sort of looked like we were pushing the fire with our hose stream. That's not exactly the case, right? So let's watch a video here and see if we can tell as they go in, they're going to do that flow and move, but they're going to be sealing off the flow path as they go in. So right now you can see that you've got an exhaust path over the top of their head, and certainly you've got an exhaust path out that window where the fire's blowing out of there. As they go in, they're going to do a wall sealing wall. So they're going to start moving that hose line in that U shape, coating the walls and the ceilings. You can see they just started doing it because they sealed it off. They sealed off that exit flow path. Okay, so you saw how the water, how that smoke and stuff that's coming out the door they went in got sealed off. Now they're at the fire room putting the water on the fire. So as that we can hose stream can alter those flow paths. So we just have to think about that. Keep that in mind. How are we altering the flow path? If we alter the flow path, we change where it's exhausting at, that may cause the fire to go to a different location within the building because the fire is producing high pressure inside the room. And that high pressure is looking for a low pressure area to get out because nature always balances itself, right? So if it's got a nice path where it's exiting out the building and then you block that off somehow, that high pressure is going to force it somewhere else in the building to try to find the exhaust. Maybe it's going to be in the way of you going to the fire. So we just need to think about that, how using that hose line can seal off that flow path. Okay. Here again, looking at it a little bit different angle. If you're using that fog pattern, which is what they're going to do this evolution, this time they're going through and they're going to use that narrow fog. They're going to move in an O pattern. You know, they're not going to get the surface cooling that we would get using that smooth bore directed, high. Because of that, you're going to see how the fire reacts a little bit here. All right, so they're going in, they've sealed off that exit flow path. Uh, you see it happen in the doorway that they went closed in there. But look at how the fire reacts. Okay, look at the steam generation pushing those big clouds out that window. Okay, so different approach, different consequences to using a different style. Um, of hose stream, right? So again, we're pointing you towards using that jet stream of that smooth bore. What shouldn't we do? Um, you know, the combination nozzle set to that narrow fog. We're trying to avoid using that. If we're doing the outside opening, we don't want to use it on that fog pattern. We want that straight stream, and we don't want to whip that hose around with a lot of movement. We want to direct it in the room, steep angle, and don't move it around so that we're not entraining air, so that we're not blocking that opening. Okay. Um, because that can cause other things to happen, right? So there they're doing it at that wide fog pattern, whipping that around. And here, look at what it's doing to the fire, pushing it out from a different opening in the building. All right. Because we've blocked that off, changing the flow paths inside, we've made the fire worse in other parts of the building because we weren't using appropriate techniques. Right. Speed of the transition. Um, this is what we're calling sort of the enemy of regrowth, right? So if we're doing this rapid application of water from the exterior, you sort of follow them through. Uh, in the pictures, in the series of pictures. So they're applying the water, the top row at the far right side, the fire's what we call darkened down, right? They've cooled it off, but the fire's going to come back. Okay, fire's going to keep going because we've cooled all the surfaces in the room. The gases have contracted. We've only got a limited amount of time to get back in and finish the fire off. So we need to make that rapid transition from the exterior water application to the interior water application. So how do we do that? Maybe that's that we pull two hoses and that we've got two lines ready to go. One does the exterior when the exterior is done, the interior is going. We're coordinating that. Okay. Maybe it's that we change what we do after we do that. So here we've done that steep angle in the window, and then on the left-hand side, it says half bale whip. What that's talking about is we've applied the water at the steep angle through the window with our branch all the way open using that jet stream, the smooth bore directed at the ceiling. Then you can go up to the window, only open halfway, which is going to disperse the water and get that in there and whip it around so that we get more dispersion and more coverage and get that fire knocked down there from the exterior. If we can't do that quick transition to the inside, here what they're doing on the right hand side after they've applied the water, steep angle to the ceiling, cooled all the surfaces inside the room, then they're bouncing it off of the window frame to disperse the water and to get it to rain down onto the burning materials inside the building. Okay. So just using sort of different techniques there to keep the fire knocked down. Where and how do we do this transition? You know, do you enter the building from the front door every time, or do you enter from the closest door to the fire? Do you use one line and you put that from the exterior and then take it inside, or do you use two lines at the same time? Um, it mentions booster line versus hand line. Be careful. Booster lines that you guys have that I've seen on your equipment are high pressure with a fog nozzle. Not at all what we want to do using these techniques. We don't want tiny droplets of water. We want those big droplets of water. Again, see last week's training where Mark talked about um, choosing that jet stream smooth bore over the fog or the combination, right? And then here, crew versus apparatus operator. In the department that I came from before, we had our operator pulled a line and put the exterior water application. That was the responsibility of the driver, was to get the pump up and running and to apply water from the exterior, while the rest of the crew prepped to go interior. All right. I'm in a new department now. They don't do things quite like that. Uh, they're using a different style engine and things like that. So they've got a different technique that they're doing, right? And this water mapping that I'm teaching you guys today is something I'm taking my new department through to learn these techniques. We're going to be buying new different branches because of this research and this information. So really sort of a timely subject for me to be teaching. I'm teaching you guys here online in Africa. I'm teaching the same thing back here home in the US, right? So, quick review of what we talked about, and then I've got some summary videos to show you. I'm actually doing really good on time here. This is cool. Uh, Air entrainment that we talked about. Don't let this video sort of deceive you, right? We're seeing that fire being pushed through the stairwell. That's because they entrained too much air, used a fog pattern on the window, pushed all that air in there. If we're not careful, if we're using a fog stream and really whipping that branch around, it's the same as putting a electric fan or a gas powered fan, putting a ton of air into that building. Be cautious. Use the air entrainment to your advantage. and make sure that you're not doing it to the detriment of the fire or to the people that are inside. Okay. Water mapping, how does that water move through the building? Perpendicular streams, we spray that stream directly at the wall. It's radiating out 360 degrees, running against the wall till it hits another wall, or gravity pulls it down. Applying that water at a steep angle provides the greatest surface coverage in the room. I don't know how many times I've said it so far today. I'm going to keep saying it till you get tired of hearing me say it. Apply the water, steep angle to the ceiling. Okay. That gets limited water to the center of the compartment, though. So we've got to follow it up, either from the interior or the exterior, to make sure that we get the fire out. If we hit the window header at a steep angle, that'll diffuse that water and get it onto the center of the compartment some to help minimize that regrowth. We can use the door frame to get water into that compartment early before we arrive. So we're going down the hallway, we're moving the wall, ceiling, wall. We're entraining some air with that, but that's help pulling fresh air behind us as we work our way in. Then we see that door frame. We're bouncing it up and down off of that door frame, starting to knock down the fire in the center of the room. When we get to the doorway, where are we putting the water? Steep angle at the ceiling, covering the walls and the ceiling, getting that rapid cool down, gas contraction. Then we're putting the water on the stuff that's actually burning in the room. All right. So there you go. That's sort of the summary of the water mapping. Exterior application. What are we doing? Using that steep angle to provide the maximum surface cooling, following it up so that we prevent the regrowth or limiting the regrowth of the fire. We want the maximum amount of water going into the room with the least amount of air. So we're using that jet stream. We're using that straight stream. We're not moving it around. We're not whipping it around in the window. And we're certainly not doing anything with a wide fog pattern that's going to block off that whole opening. Right? When we're inside, what are we doing? We're going to try to do that flow and move. That's going to improve things for the victim inside, okay? And for us behind the hand, operating the hand line. Flowing and moving, we're taking advantage of that air entrainment. We're moving fresh air in with us as we go. We're using either an O pattern, so we're covering floor, wall, ceiling, wall, floor, wall, ceiling, wall for that maximum surface cooling, or we're doing the wall, ceiling, wall pattern, the upside down U. Those are the patterns we're using as we're moving through the building, cooling. Remember that smoke that we see over the top of our heads, that's unburnt fuel that's waiting for us to make a mistake, right? And then that high initial application into the fire compartment, all right? Coat the surfaces, get everything cool initially as we go in there, and then work on the burning materials, all right? What's the grand finale? If we water map properly, proper application, that's what wins. Whether we're doing exterior and interior, it matters, all right? Contraction outweighs expansion with solid and straight streams. So gas contraction that we're going to get by cooling all the surfaces around the fire is going to work better for us than the steam expansion using the broken fog stream. Okay. A total water needed for 2 rooms post flashover is minimal. So if we can reduce the, we do that proper exterior attack, we set the fire, get us to where a flashover is not going to take place, then usually we can finish off the room with less than 750 liters of water. All right. So what do? We knock back the fire from the exterior. We knock it down off the plane, right? We're hitting the surfaces, knock it down on the plane, bouncing it off of something to cool the inside part of it, right? Then we're getting into the base fire, getting the branch somehow in that room to wet the rest of the materials to get the fire out, all right? Whew, that was a lot of stuff. I was talking fast. Gonna show you a couple videos. I got a series of 4 videos here It should, maybe we're going to go over by just a couple minutes, but we're gonna watch this and see what happens here. So here's just a summary of everything we sort of talked about here.
Understanding the fundamentals of hose stream mechanics is vital to the success of fire suppression operations on the fire ground. This includes knowing how and when to utilize air entrainment to your advantage, understanding when air entrainment can be your enemy, and understanding how to best apply water through various application patterns, stream angles, and deflection methods to successfully map the compartments inside a structure. Before discussing the impact of air entrainment on suppression operations, we must first understand how a water droplet moving through space entrains air. As the bail of the nozzle opens and the water leaves the end of the nozzle, the momentum of the hose stream propels the droplets forward. As the droplets impact the air ahead of them, an area of high pressure is created. In the wake of these droplets, there is now an area of low pressure, which causes surrounding air to be pulled in and carried forward with the droplet in an attempt to equalize the pressure. The air drawn in by these moving droplets is known as entrainment. If we visualize how many droplets make up a typical hose stream from either a smoothbore or combination nozzle, the potential impact and magnitude of air entrainment should be clear. In short, how we manipulate a hose stream inside a structure can change the amount of air that is entrained and has the potential to significantly affect fire dynamics and victim survivability during suppression. Now let's take a look at water mapping, or how water is distributed within a compartment. Surface cooling is vital to the success of extinguishment, stopping the heat absorption and subsequent re-radiation of the hot surfaces back into the compartment, which contributes to the heating of fuels, speeding up fire growth, and transition through flashover. Learning how to employ different stream types, application patterns, stream angles, and methods of deflection will assist the nozzle operator in game time decision making to most effectively distribute water and map the surfaces inside a compartment during suppression. Coupling together the concepts of air entrainment in hose streams and the principles surrounding effective water mapping in structures will enable firefighters to most effectively apply water on the fire ground to maximize the potential survivability of trapped occupants and quickly suppress the fire.
All right, so next we're going to look at exterior water application. All right, here we go.
Applying water from the exterior of a structure into a fire compartment requires a solid understanding of the impact of air entrainment and water distribution. As we begin to discuss the principles of exterior suppression, let's take a look at how the angle in which the stream is applied will affect the distribution. If we apply a hose stream perpendicular to a surface, the water will radiate in 360 degrees. We often picture that as a stream applied straight ahead towards a wall, but now let's imagine that stream applied to the ceiling surface of a compartment. The shallower the angle into the compartment, the more water that will be propelled forward towards whatever wall or obstruction is opposite the opening in which the water is being applied. This does not provide any surface cooling to the ceiling or walls that are nearest the ventilation opening where most of the burning is occurring. The steeper the angle into the compartment, the more water will radiate outwards in all directions, providing better surface coverage and better cooling. As the stream impacts the ceiling and the water radiates outwards, the momentum of the water carries it across the flat ceiling surface common in most residential structures. Once the water has coated the ceiling surface and reaches the side walls of the compartment, it falls down these surfaces in sheets. As the water reaches the floor, it now accumulates in pools in different areas depending on the obstructions that may or may not be present. This water application method nearly simultaneously coats all surfaces within a compartment and is extremely effective in suppression. During fire suppression, initially employing a steep stream to coat all interior surfaces simultaneously will rapidly reduce temperatures inside the fire compartment. The drop in temperatures causes the fire gases to contract, decreasing pressure, lowering temperatures, and improving survivability in adjoining spaces. Once the interior surfaces have been cooled and we have begun to knock down the fire, we must focus on getting water into the middle of the compartment to limit the likelihood of regrowth. If we are located on the same level as the fire, the nozzle can simply be inserted in the window and additional water can be applied to the remaining burning fuels. If we are located 1 or 2 floors below the fire, the hose stream can be deflected off of the window header or lintel to achieve additional distribution, followed by entry into the structure for final extinguishment. It's important to understand that utilizing a straight or solid stream during exterior water application is essential to ensure that we get the most amount of water into the compartment with the highest momentum, the largest droplet sizes, all while entraining the least amount of air. We must also ensure that the window opening is not occluded with the hose stream. An occluded vent will prevent the opening from serving as a low-pressure exhaust for the fire gases. Thus, the fire gases will be redirected to another low-pressure outlet within the structure. This is commonly referred to as pushing fire. Keeping the hose stream in a straight or solid pattern will limit the amount of air entrained and not disrupt the gases outside the fire compartment, whereas a fog stream employed into the opening will cause fire gases to move about the structure and potentially impact trapped victims and other firefighters operating on the interior.
All right, and then one last look, one last summary video here of using the attack tactics we just talked about in the inside.
Past research has shown the importance of a flow and move approach during interior fire suppression for the survivability of trapped occupants and the safety of operating firefighters. This approach allows us to take advantage of maximum surface cooling while utilizing a moderate amount of air entrainment. Let's begin by taking a look at air entrainment values with different stream types and application patterns. Suppose that you are positioned at the start of a hallway holding a straight or a solid stream aimed downrange in a fixed position with no manipulation. In this case, you are entraining about 1 to 2,000 cubic feet per minute of air into the stream. As soon as you start to manipulate that stream into an O pattern, you increase the air entrain to approximately 4 to 6,000 CFM. This will occur regardless of the type of pattern chosen and is more dependent on the speed of the application. If we now change from a straight or solid stream to a fog stream, the air entrainment increases dramatically. For example, a narrow fog stream held fixed entrained approximately 10,000 CFM of air. If we now manipulate that fog stream into an O pattern, we can expect to see the air entrainment in excess of 15,000 CFM. This magnitude of air entrained with fog streams can be comparable to that of a positive pressure fan. It is important to understand that these values are similar regardless of whether you choose a straight stream from a combination nozzle or a solid stream from a smoothbore nozzle. Air entrainment in hose streams is less dependent on the flow and nozzle pressure and more dependent on the movement of the stream and the speed of the pattern chosen. As we have learned through the suppression studies, straight or solid streams maintain large enough droplets to ensure the maximum amount of heat is absorbed and the most amount of surfaces are cooled. In contrast, utilizing a fog stream may be effective at absorbing heat from the gas layer, but the size of the droplets do not allow for sufficient surface cooling. With minimal surface cooling and maximal air entrainment, fog patterns are not an effective stream choice for initial knockdown of a post-flashover, ventilation-limited fire. One successful means of extinguishment is to employ an O pattern on the advance to a fire compartment. During a flow and move advance, this pattern can essentially seal off the space ahead of the advancing hose line, taking advantage of air entrainment to draw fresh air in behind. This will prevent the products of combustion from coming back over the firefighters while allowing the higher temperature, higher pressure gases behind the firefighters to ventilate out of the structure. Venting of the gases behind the advancing crew will improve survivability for trapped occupants and visibility for searching firefighters. Applying an O pattern on the approach to a fire compartment will ensure that the surfaces are cool and will limit the thermal exposure to the nozzle team on the advance. Water applied in the hallway is simply used to help the nozzle team get to the fire compartment safely and begin to take control of the space. However, water applied in the hallway will not be able to map surfaces inside of the compartments. Once the nozzle team has an idea of the location of the fire, attempts should be made to get water into the compartments as early as possible. This could include deflecting the hose stream off of the door frame of the fire compartment for early water application onto the seat of the fire. As the nozzle team reaches the threshold of the compartment, the same approach to that of exterior water should be taken. An initial steep angle will coat all surfaces in the compartment. Once the fire is darkened down, the stream can then be brought lower onto the remaining burning fuels. After the fire is extinguished, the nozzle team should employ hydraulic ventilation out of any available opening to aid in smoke removal from the structure.
All right. I think we're gonna call it quits there. We're at our time limit here. Covered everything that I was interested in covering there. There's one more video about hydraulic ventilation. Maybe we'll take a look at that later on in tea time or something. But thank you all for joining us for today's training. If you've got questions, please stick around a couple more minutes as we transition into our tea time. We'll get those questions answered for you. Thanks for coming along to our training. Check out Africa Fire Mission on YouTube. You'll be able to find a recording of this if you'd like to go back and watch it again. Go to our webpage, www.africafiremission.org. Go to the Resources tab and Training Materials. Go to the 2025 Virtual Trainings. You'll be able to find this. If you want somebody else to learn this material and you'd like them to get a certificate for it, you can do that. Go to that Google Drive folder, answer a couple questions, watch the video. We'll get you a certificate for that training as well. Thank you all for coming. We got plenty of seats here. If you find that there's somebody that that may learn from what we're doing here, be sure to share that registration link with them. That's all for today. Stick around for tea time. I hope to see you all again next week.